Welcome to Digital Electronics lecture series. This is lecture number 11 and we'll be starting with Boolean algebra and logic gates. So we already studied in the previous lectures what are the various numbering systems, and now we'll see some basic operations of electronic circuits, then the basic building blocks. So first of all we need to study Boolean algebra. So all digital electronic devices are based on use of digital logic circuits, and logic circuits, they are based on logic equations which are also called as Boolean equations. And logic circuits, they operate in binary mode, either it is 0 or 1. Therefore we study this binary numbers, and in order to understand the logic circuit we must also study Boolean algebra. And because Boolean algebra, it is used for analyzing and designing digital circuits, so we can design the circuits using this Boolean algebra. This Boolean algebra was designed by George Boole, one of the mathematician. Then here we see logic operations. Logic algebra is suited for any system which is based on these two opposite states. Either it is logic 0, either the state is logic 0 or it is 1. Either it is true or it is false, or it is low or it is high, off, on, no and yes. So generally we will be using this true false notation, or maybe this low high. Then in Boolean algebra there are three basic operations. First is logical addition, which is called as OR operation, capital OR operation. This is denoted by symbol or plus sign, so OR is represented by a plus sign. Then we have logic multiplication, which is the AND operation. So AND operation is represented by this AND, a dot. And we have logical complementation, which is called as NOT. It is represented by a over bar, this one, like we have this A bar. And for example, this OR operation, we can have A or B. So this is not plus but is OR. In logical language or Boolean algebra, this is OR, and this is A and B. And this is, we can have either A bar, B bar, anything. This is A bar or B bar. We can also write any complement. This is complementation of B bar. Next we come to logic. We start with logic. So there are three basic operations in logic: AND operation, OR operation, NOT operation. We will see these operations using switches first and then the actual gates. So how we can represent these gates, these operations, by using switch and a small lamp, and then we will see how this is actually working in the case of the. So here we see the analogy of a AND gate. First of all, we see this is to switch, this is the lamp, and this is a power supply. So when we make one input, this both inputs are 0 0. This open switch, this is open switch, this is a close switch. Open switch, so open means 0, close means 1. So when both are open switch, that is 0 0, the lamp does not close. When we make this one 1, still it does not close. We make this open, this close, still does not close. But when both are closed, so for 1 1 we say close means 1, open means 0. So when both are closed, this glows. Now let us check for the AND gate. Both input are 0 0, open switch. Then we make one the upper one as 1 and then close it. Then 0 1 1 0, it does not close. But when both switches are closed, 1 1 is 1. So what we say is 0 0 0 0 is 0. Then 0 1, then 0 1 is again 0. Then 1 0, so this is 1, this is 0, 1 0 is again 0, and 1 1 is 1. So this is how we represent the AND gate, the working of the AND gate. Now let us check the working of a OR gate. So here we place the switch in parallel, and here we have the OR gate. So for 0 0, both are 0 0. Now let us make one of the input as 1. This is 1, so we get 1 here. When it is glowing, it is 1. So here 0 1 is 1. Now what about 1 0? If I make it as 1 0, so for 1 0 it is also 1. So I make this as 0, this as 1. So 1 0 is also 1. Both are 1. It is also 1. So for 0 0 we are getting 0, and for all the other input conditions we have 1. Output is 1. Next we see the working of a NOT gate. So left side is the circuit description, and right side we have the gate itself. So when the input are 0 0, you can see open switch is out 0 input. So here also 0 input, output is 1. Now when we close the input, when we go input as 1, output becomes 0. Here also output becomes 0. So for when the input is 0, output is 1. So this is how the NOT gate works. Now let us summarize what we have done. So AND gate has 2 or more inputs but a single output. So AND gate can have 2 or more inputs, or but output is only 1, irrespective of the number of inputs. Then the output of AND gate is high, that is logic 1, if and only if all the inputs are high. So if we have a 5 input AND gate, 5 input, and even a single input is 0, output becomes 0. So to make output as 1, all the inputs should be 1. Now this is how we represent. This is this y equal to a and b. This is the we can say the Boolean expression or the logic expression for AND gate. And this is how we represent the AND gate. This is the symbol for AND gate. So here there are 2 inputs. We can have more inputs. Then regarding the truth table, now let us draw the truth table. So here we are drawing the truth table for a 2 input AND gate. So for 2 inputs we can have 4 combination. The 4 combinations are 0 0, 0 1, 1 0 and 1 1. So here 0 1 0 1, 0 0 1 1. So this y equal to a and b. So this is 0, this is 0, this is 0, and finally 1, because all the inputs are 1 in this case. So this is how we can represent the working of an AND gate. Now next is OR gate. So OR gate has 2 or more inputs but a single output, similar to AND gate. But here the output of OR gate is high, that is logic 1, when any of the input is high. So if we have a 5 input, suppose we have a 5 input OR gate and one input is 1 and remaining all the inputs are suppose 0, then also output is 1. So to make the output of a OR gate as 1, even a single input 1 will make output as 1. So to make it as 0, output as when we want to make the output as 0, all the inputs must be 0. Now this is the representation, the Boolean expression for OR gate, y equal to a. This plus means OR, a or b. This is the symbol of a OR gate. Here there are 2 inputs. We can also have more than 2 inputs. So this is the output. Then let us see the truth table. So we draw the truth table for a 2 input OR gate. So here we see there are actually 4 combinations, 0 0. So 0 0 is 0 and rest all in outputs are 1. So this is how the OR gate works. So now next is the NOT gate. So NOT gate has 1 input and 1 output, and the output of NOT gate is always the complement of its input. So what do we mean by complement? That if input is low, output is high, and if input is high, output is low. So 0 input, 1 output, 1 input, 0 output. Then this is how we have the Boolean expression y equal to a bar. We read it as a bar. And this is the symbol of a NOT gate. There is a bubble here. Okay, so input is a, y equal to a bar is the output. The truth table of a NOT gate. So because we have only single input is there, so we can only make two combination, 0 and 1. So here output y equal to a bar, we will see this a bar, so 0 input 1 output, 1 input 0 output. So this is the working of the NOT gate. Now until now we studied 3 gates, AND, OR, NOT. These 3 are the basic gates. Now we can combine this basic gates to form some more gates. The first we see is a NOR gate. So NOR gate is a combination of OR and then we have NOT gate. We will see the symbol afterwards. So NOR gate has 2 or more inputs but a single output. It can also have 2 or more inputs. And the output of NOR gate is high, that is logic 1, if and only if all its inputs are low. So to make this to make the output as high, all the inputs must be at low, otherwise the output will become low. So this is opposite of OR. It is opposite of OR. OR is 0 when both the inputs are 0 and NOR is 1 when both the inputs are 0. Now how do we represent this is the Boolean expression y equal to a or b the whole bar. So this is the whole bar, and this is the symbol of a NOR gate. You can see here we have a OR and then a bubble. So actually if we want to make a OR NOR gate, we can just have this is a NOR, this is a OR gate, and then we can put a NOT gate add of it. So this becomes, this is A, B, this is at this point we have A or B, and NOT gate is A or B the whole bar. So this is the combined, this one is the actually combined symbol. This is actually we represent, this is how we represent a NOR gate. This is how we represent it. Now let us see the truth table of a NOR gate. The truth table of a NOR gate, this is what we have. Y equal to, just change the pen, y equal to, so y equal to A NOR B, A or B the whole bar. So 0 0 is 1, rest all are 0. So this is exactly opposite of a OR gate. Now next is a NAND gate. So NAND gate is a combination of a AND gate and NOT gate. So NAND gate also has a 2 or more inputs but a single output. And the output of a NAND gate is high, that is logic 1, when even a single input is 0. So if a single input is 0, output becomes 1. That is, this is opposite of AND. In AND, when a single input is 0, output becomes 0. But in NAND gate, when a single input, even a single input becomes 0, output becomes high. This is the Boolean expression of a NAND gate, A and B the whole bar. And this is the symbol of a NAND gate. There is a bubble here after AND gate, so it is equivalent. We can say it is actually how we make up a AND gate is we have a NAND gate, that is we have a AND gate, and after this AND gate we have a NOT gate. So this makes up a NAND gate. So this is AB, this is A dot A, this A and B, and this A and B the whole bar. This this is NAND gate. So this is actually equivalent to this one. So this is how we make up. Now let us see the truth table of a 2-input NAND gate. So with 2 inputs we can have 4 combinations. So here Y is A and B the whole bar. So any of the input is 0, output becomes 1. This is 1, this is 1, and this is 0. So when all the inputs are 1, output becomes 0. Next is XOR gate, which is also called as exclusive OR gate. So XOR gate has 2 or more inputs but a single output, and the output of XOR gate is high, that is logic 1, when odd number of inputs are high. So let us take an example. Suppose we have a 3 input XOR gate. And the inputs are given in such a way that the first input is 0, the second is 1, the third is 1. So in these 3 inputs, the number of inputs high are 2. So 2 inputs are high, 2 is a even number, so the output becomes 0. So this is how it works. Let us take one more example. Suppose we have a 5 input XOR gate, 5 inputs. There are 5 inputs in the XOR gate, and the first input is 1, the second is 0, the third is 1, the fourth is 0, and the fifth is 1. So these are the input combination. So here we see the number of inputs high, 3 inputs are high. So 3 is an odd number, so the output will be 1. So this is how XOR gate works. So number of inputs are if odd number of inputs are high, output becomes high. This is the how we represent this is the Boolean expression of a XOR gate, A XOR B. So this is a plus this sign and then a circle over that. So this is the XOR gate, and this is the symbol of a XOR gate. This is how we represent XOR gate. And then how do we draw the truth table of XOR gate? So for XOR gate, we have the representation y equal to A XOR B. So first case 0 0. So number of inputs which are high is 0. 0 is a even number, so this becomes 0. Now 0 1. Number of inputs which are high, 1 is high. 1 is an odd number, so this becomes 1. Same is the case in the third one. 1 input is high, 1 is an odd number, 1. In the fourth case, 1 1. 2 inputs are high. So number of inputs high is 2, which is an even number, so this becomes 0. Now this is how we can construct a XOR gate using the basic gates. So this is actually a XOR gate. This entire will work as XOR gate. We just saw the symbol of XOR gate, but this is how XOR gate is constructed. So here how we do that, this is A goes here directly, so this becomes A here, this is A, and here A comes with a NOT gate, so this becomes A bar. Then here we have B, so this directly goes to the AND gate, and here from here this part it comes here with a NOT gate, so this becomes B bar. So here we have A and B bar, and here we have A bar and B, and here we have OR operation. So finally what we get is A B bar or A bar B. So this Y output is A B bar plus or A B, which is equivalent to A XOR B. So this is the XOR gate working. So that's all for this session. Thanks for watching.